An altitude camp has become an essential part of race preparation for many elite endurance athletes. However, is an improvement after an altitude camp a sure thing, either across a whole team or even within the same athlete? In today's episode, we'll take a look at whether hemoglobin, the molecule in red blood cells that carries oxygen in our bodies, increases consistently across a wide range of elite endurance athletes after an altitude camp. Also, were there any predictors for better odds for improvement? Before major competitions, endurance athletes like cyclists, runners, and cross-country skiers will often spend weeks living and training up at altitude. One of the main ideas why this may be beneficial is that the lower oxygen at altitude causes the kidneys to produce and release the hormone erythropoietin, also shortened to EPO. This then acts at the bone marrow, which is where hemoglobin and red blood cells are produced. So when you come back down to lower altitudes after a few weeks, theoretically with more hemoglobin, your body can then transport more oxygen, allowing you to exercise harder and longer. But after over a half-century of research, it's still unclear whether this increase in hemoglobin is a real and consistent response to altitude training across or even within the same athlete. Also still in debate are the ideal altitude and duration of altitude camps and how to optimize them for individual athletes. To study these questions, Nummela and colleagues tracked the hemoglobin mass changes in 59 elite Finnish endurance athletes over the course of 82 individual altitude camps. These camps range from 1350 to 2500 meter elevation over anywhere from 16 to 42 days. Most camps involved living at altitude and then training at either altitude or lower elevations. As iron is a key component of hemoglobin, supplementation was recommended but not always done. Importantly, 15 athletes performed 2 or more altitude camps in this dataset, allowing the researchers to study whether hemoglobin mass changes were consistent within the same athlete. Let's first look at how the entire dataset looked. The minimum increase in hemoglobin mass to be considered a positive benefit was 1.7%, as this was the sensitivity of the hemoglobin test. Remarkably, a positive response was seen in only 56% of the 82 camps. The percentage of positive benefit was improved when only looking at camps at 2,000 meters or higher, and also where iron levels were at a good level before camp, suggesting that these are two important criteria to consider when planning altitude camps. Further, while the percentage of positive benefit was similar between males and females, males in general had a higher increase in hemoglobin mass. So hemoglobin mass increases was not a consistent response across athletes. But what about within an individual athlete? The results here are surprising. Of the 15 athletes with more than one camp, only 4 showed a consistent positive hemoglobin mass increase, while the other 11 showed highly inconsistent responses of both positive and no or even negative responses. This highly variable response may be due to some of the factors we've discussed, like different camp altitudes and duration, along with iron levels. But it really highlights how a positive benefit from altitude training is never guaranteed. Therefore, both the athlete and their support team have to carefully plan for best odds of success, including closely monitoring responses throughout a camp and making adjustments as needed during the camp. I hope that you've enjoyed this look into the fascinating world of environmental physiology. I'm Dr. Stephen Chung, and I run the Environmental Ergonomics Lab in the Department of Kinesiology at Brock University in Canada. We post new short videos on different aspects of environmental physiology every Wednesday. Thanks for watching. See you next time.